I hope that Luca explained you a little bit better what I mean with this notation. Okay? I want to warn you. You must distinguish the vector space and the points in the Lagrangian configuration and the points and the vector space in the Eulerian configuration. If you don't distinguish them, you will soon lose the meaning of what we are doing. So, I will try to follow this notation. Everything capital is Lagrangian, and everything small is Eulerian. So, for instance, if I have a linear map from the Lagrangian to the Eulerian configuration, this is a vector capital B. You have a linear map and you have a vector small b, which is equal to LB, capital B. So this is a segment of material particles, and this is a displacement from one position to another position. This is the position occupied by the point X, and this is the position occupied by the point X plus B. And I'm summing up points with vectors, getting as a result a point. Okay? So the idea is, if I have a point and I add to a point a vector, I am moving along the direction of the vector and I'm falling in another point. Okay? So, what we have, maybe it is better if we try to give an idea of the proof of the theorem about isometry, which I formulated this morning. So what do we know? We know that if I choose x naught, this x naught is placed in small x naught. So the replacement chi is preserving distances. Okay? So every triangle is mapped from a triangle in the reference configuration to a triangle in the actual configuration. The lengths of the sides are the same and the angles are the same. Okay? So you have one point, a second point, and a third point. These 3 points are mapped in 3 points. Every side of this triangle has the same length as the sides of this triangle, and every angle between 2 ordered sides is the same. Why? Because K is an isometry. Okay? Now, if K is an isometry, then the inner product between these 2 vectors and the inner product of the images of these 2 vectors is the same. Because this length is the same, this length is the same, and the angle is the same. Okay? Okay. Now, the difficult thing is the following. I must prove that this is a function of capital V. So I choose x0, and then I have x0 plus v. I calculate the position of x minus the position of x naught. This is a vector. And I call this vector f of v. So I have a map which takes a vector capital V, and to this vector capital V associates a vector small v. Okay? Now, what I'm telling is so easy that you could believe there is a trick, but there is no trick here. So we have V1 inner product V2. I take two vectors. So V1 is equal to kx1 minus kx0. And this is inner product with kx2 minus kx0. Okay? And this is equal to, with our notation, f v1 inner product f v2. So the application f is as a trivial consequence of our reasonings, starting with the assumption that K is an isometry, preserving the inner product. Okay? So what can we do? We can choose for V1 the generic vector V, and for V2 the generic vector EI in a basis of the vector space. And this is equal to FV inner product FEI. I am allowed to do this. Okay? Now, I claim that this equation implies that f is linear. For proving this, I simply need to remark something. EI is a basis. Orthonormal basis we can choose. Okay? What about FEI? It is an orthonormal basis. Why? This is true for every V. Okay? So I can write it for EI. EI dot EI equal FEI dot FEI. This is one hypothesis. FEI dot SPI equal 1. So FEI is a unit vector. Okay? Then instead of V equal EI, I can use EJ with I different from J. Our hypothesis is that this is equal to 0. And we prove that FEJ dot FEI is 0. So what we have proven, that the image under F orthonormal basis is an orthonormal basis. Okay? We have nearly done. Because now I take a vector V. This is equal to sum over I of alpha I EI. What is alpha I? This inner product. Okay? FB is equal to sum over I of beta I F EI. Okay? And beta I is this inner product. So, I take alpha I, and this is equal to beta I. So I can calculate easily beta I in terms of alpha I. It is the unit matrix 1, 0, 0, 0, 1, 0, 0, 0, 1. I calculate this times alpha 1, alpha 2, alpha 3. What I get? Beta 1, beta 2, beta 3. This is a linear function. It is represented in a given choice of one basis from the starting vector space to another basis of the arrival vector space in terms of a matrix. Okay? If we have done this, we have nearly ended. So F is linear. So let us write everything. L of capital B, inner product L of W, now these are linear functions, is equal to V inner product W. Okay? You should have understood that this is the inner product in the Euclidean space, and this is the inner product in the Lagrangian space. Okay? Now, do you remember the definition of the transpose I have given to you? With the capital and small letters you understand quickly. The application of A to a capital vector gives you a small vector. and you calculate its inner product with W, small. The transpose of A takes a small vector and it transforms it into a capital vector. And here you have the inner product between capital vectors. Okay? So the transposition allows you to jump from one side to the other of the inner product. Okay? We will write slowly also with indices. Okay? So here I can jump this way. So this is equal to L transpose L V dot W. So remember, L of a capital vector is a small vector. L transpose of a small vector is a capital vector. This is a correct equation. Okay? Now, what is strange, you maybe ask yourself, why this morning I started talking about the properties of zero. Okay? Now you discover why. You know, when I usually try to teach this to my students, they are crazy because they become crazy because for them this is easy. You take this animal on the left side of equal and you get equal 0. Then it is already a little bit difficult to factorize W to get L transpose L V minus V dot W equals 0. Okay? But this is algebra. Inner product is distributed with respect to the sum. Okay? Now we have a problem. Which is that vector such that its inner product for every times every vector gives you 0, or in other words, which vector is orthogonal to all vectors? Only the vector equal to 0. I mean, the vector 0. I think that in English you can say the neutral element with respect to the sum in the vector space. So the vector which added to every vector leaves it unchanged. Okay? So the only vector which is orthogonal to all vectors in an Euclidean vector space is the null vector. So this is 0 as a number. When I erase this is 0 as a vector. Okay? Now you need Rouchet-Cavalli. Why you need the theorem of Rouchet-Cavalli? Because I hope that you know that row times column product is not commutative. So you can factorize the. Okay, before factorizing. The identity maps a vector into itself. and it is represented by the identity if you have the same basis starting and arriving. Okay? Here, finally, you can factorize the on the right. So what you have? That the linear map L transpose times L minus the identity is equal to 0. And this is true for everything. Now, you have a linear system. The set of solutions of this linear system is made by all vectors. So, if you write this in terms of a basis, you have a matrix of coefficients which represent this linear map, and this matrix of coefficients times every row times column, every vector v equal to 0. So this homogeneous linear system admits as a solution all the vectors in your vector space. What you can tell about the rank of this matrix? This rank has to be 0. This is a consequence of Boucher-Capelli theorem. Okay. The only linear system which admits the whole set of vectors as a solution of the homogeneous equation is made by the matrix with all zeros. Okay? So if you have doubts about this, try to reconstruct these passages, or maybe we can talk about this tomorrow in detail. Okay? So, we put this final relationship. L transpose L minus identity equals 0. So, L transpose L equal identity. L transpose equal L minus 1.
Is it 1 or?
No. This is the identity. So this is the linear map which maps a vector into itself. In a basis, this map is represented by the matrix 1, 1, 1 in the main diagonal and 0 in the other end. Okay? So L minus 1, L equal identity, and this implies that L minus 1 equal L transpose. You understand why people are so strongly interested in orthogonal matrices or in orthogonal applications. Because orthogonal applications are those applications which preserve the inner product and which preserve the distance between every pair of points from the domain to the codomain of a given point. So we can do a resume. If you know that the application map K preserves distance for every pair of points, then K is equal to k of x0 plus q x minus x0, where q is a linear orthogonal member. This is what is called the formula of rigid placement. Rigid placement is a placement for which the distance between points is preserved. Okay? So you get a very general representation formula which is valid for every placement preserving distances. So if you have a body and it keeps its shape unchanged, then the placement must be given by this form. If the placement is changing the shape, then this formula is not valid. So this is the power of this formula. It gives you a necessary and sufficient condition for the invariance of shape. So if you want to study deformation, then you are obliged to understand the absence of deformation. Okay? Okay. So, my suggestion is the following. You must understand all details of the reasoning I was developing. So repeat it until you understand them. Because if you want to study the deformation of the bodies, you must be able to understand perfectly the placement which are not changing the shape. Okay? Now we try to understand what is measuring deformation. So our aim now is to try to introduce the measure of deformation. Because either a body is not deformed, or if this formula is not valid anymore, it is deformed. We need to measure how much it is deformed. Okay? Because in order to write mathematical formulas, we must be able to say how much. I mean, when you measure weight, you say 1 kilogram, 10 kilograms. 10 kilograms is heavier than 1 kilogram. So we must try to say that something is deformed and how much it is deformed. The bad news is that we will discover that the measure of deformation is given by a linear method. The good news is that we can measure the deformation. So one number will not be enough for measuring deformation. You will need many numbers. This is the bad news. So you have to change your point of view. You cannot measure deformation telling 10, 5, root of 3. For measuring deformation, you need many numbers. Okay? What we will discover is that we can measure a deformation with a symmetric matrix. If you have fixed a given basis, or with a symmetric linear map, if you don't want to fix campuses. Okay, this reasoning we can do. It is rather easy, but we need the concept of Taylor expansion. By the way, it is really astonishing that this reasoning has been done by somebody, I don't know, Green, Viola, Cauchy. We can quarrel about who had the idea first, but what is important is that they did it at the beginning of 19th century, and they started modern finite element theory. So finite element theory was born 150 years before computers. So when somebody asks you why you are studying this, you can answer, we don't know. We do not know. It will be useful. If somebody had stopped Cauchy telling this knowledge is useless, now we were not using finite elements. A private society must earn money now. Somebody working for university is building the future. So we are working for what will happen in the next centuries. We have to chase merchants out of the temple. Okay? This is political statement. We keep more or less secret. Take your potato. This is the theory of potatoes. I am sure that you have studied Riemann integrals. You can cut these potatoes into the union of many cubes. Of course, now one could say, no, I don't want to cut it into cubes, I want to cut it into tetrahedron. Because somebody among you knows that finite elements like tetrahedron. We can cut it in many ways. Let us start cutting in cubes. The side of these cubes is epsilon, where epsilon is small. Now you have to understand this concept of being small. So I abandon for a while this reasoning, and I pretend that you are engineers and you want to build rivets. So you have a piece of metal with a hole, and you want to build a cylinder which is blocking this piece of metal, keeping it together with another similar piece of metal. And then you have the head of this rivet which is blocking the movement, the sliding of this. So you have another piece of metal which has another hole, and then you have the cylinder in between. Okay? Then you pull it here, there, and here. This is a piece of an airplane. What you need to know? What is happening to this rivet? If it is strong enough to resist to the applied actions, what happens around the rivet in the metal element? So, will you choose as epsilon this epsilon? it is clearly too big. If you cut these big pieces, you will not be able to say in detail what is happening here around. And you feel that what is happening here around can be very dangerous. So, most likely, you will choose this epsilon. Of course, you could have a delirium of omnipotence. You can decide that you want this epsilon. Why this last epsilon is not good? Because you will need a lot of calculations. This is too much. Too many details is bad. If you are folded by millions of details, you don't understand what is happening. You know, you could be like Navier. In a delirium of omnipotence, you could say, okay, these two pieces of metal plus derivative inside are made of atoms. You could write Schrödinger equations for this set of atoms. Then you are lost, because you have how many degrees of freedom, how many atoms you have. An Avogadro number of atoms. So you have some equations which are perfect. They can tell you everything which is happening. But they are useless. Because there are so many that you cannot solve them. On the other side, you can be lazy. You say, no, I want a big epsilon, this one. If it is too big, you lose all details of your phenomenon. So what you have to do? You have to cleverly choose the right epsilon. That one which is big enough for allowing you to do calculations and small enough for allowing you to describe what is happening. Okay? Now, Viola Cauchy Green introduced an epsilon. Which epsilon? The suitable one. I cannot tell you if it is 1/10, 1/10 to the 7, or 3. Because, by the way, I should tell you 3 what? 3 meters, 3 kilometers, 3 millimeters, 3 what? Okay? So this abstraction is needed. We must be able to treat a theory with an epsilon, which is a positive real number, not specified. This is not being mathematician, we are practical engineers. You must tell me how much is epsilon. If you want to know a number for epsilon, you are tying your hands without a true reason. It depends. Okay? I was told that a colleague of mine came to a lecture and said that for engineers, 7 is equal to 5. I would have answered, if I were a student, I would have answered in this way. Okay, I sign you a check of 7,000 euros. You sign me a check of 7,000 euros. I sign you a check of 5,000 euros. We exchange the checks because they are equal. It depends. 5 can be equal to 7 if you can allow an error of 2. I mean, it is trivial, but okay. So why I chose this parameter? So we go back to epsilon. We have taken our potato. This potato has been divided into small cubes having size epsilon. Look, you are clever enough to understand that I can invent a partition of this potato with varying sizes. I can have more cubes here, less cubes there. In this moment, this is not important. Okay? So I divide this, I partition this potato in cubes having size epsilon, and then what I do, I take this cube, I take it here, I call this node x naught, and I can consider the generic point x inside this cube. If this cube is small enough, so if my epsilon has been chosen wisely enough in my particular not specified problem, okay, then I can say that chi of x equals chi of x naught plus the gradient of chi calculated in x naught times x minus x naught plus infinitesimals of the distance x minus x naught of the second one. This is the generalization of Taylor expansion for functions defined in R3 and having value in R3. Okay? So if I've seen that Luca was giving you some details about this expansion, this is the Jacobian matrix which we have already met. This is the inner product of this matrix times the vector x minus x naught, and we can decide to neglect all infinitesimal of higher order. This matrix usually is called F, capital F. Okay, so what happens to this cube if epsilon is suitably small? This cube is transformed, if you can neglect infinitesimals, into a region with parallel faces which are not orthogonal anymore. You know, linear applications map lines into lines, planes into planes. So the faces of the cube keep their parallel property, okay? The opposite faces, okay? But these three vectors, epsilon E1, epsilon E2, epsilon E3, which are the edges of the cube, are not anymore orthogonal, so they can change their angle, okay? And their length is not anymore epsilon. They can be longer or shorter. So the idea is I cut my body into small pieces for reasoning. For starting our reasonings, we assume they are cubic, and we follow every cube, and we try to see what is happening to every cube. So what I have to study? I have to study this map, which is the map which, if x belongs to x0, tells you the position of every point in this small cube. Okay? So don't learn by heart. This is valid, this equality is valid only very close to x0. This is not valid everywhere. This is the placement of all points in the epsilon cube close to x0. Nothing more, nothing less. Now we remember what we have painfully studied up to now. When this cube is not deformed, if and only if f is orthogonal. So if it is orthogonal, if f is orthogonal, then this small cube remains with the same shape. So it remains the same cube as before, with the same shape. When f is not orthogonal, it is changing its shape. Consider f transpose minus f transpose f minus identity. You can multiply this element times a given number alpha. This is not important. Okay? This element, if it is zero, the cube is not deformed. If it is different from the zero matrix, the zero linear application, then you have a deformation. For some historical reasons, this alpha is equal to 1/2. We will discover later why this is important. Okay? So, this is natural. This animal, which is usually called capital G, this animal is the appropriate measure of deformation of your cube. Now, if you consider instead of this cube, this other cube, the matrix is another one. Okay? So what you have at the end is a field of matrices. So the deformation of a body is, in this discussion, measured in terms of a field of linear applications. Okay? Now, do you agree with me that this animal is symmetric? If you write G transpose, this is equal to F transpose F minus identity transpose. The transposition is linear. So this is equal to F transpose F transpose minus the transposition of identity is the identity. And then if you remember the properties of the transposition, if you have A times B transpose, this is equal to B transpose A transpose. The order of the product is inverted. So this transposition is equal to F transpose transpose minus L. The double transposition is F itself. So at the end, this is G. So, in order to measure how a small cube is deformed, what you have to do? You take K, you calculate its gradient, you get F. This F is a different F in different points. You can build F transpose F minus identity. Okay? If this is 0, there is no deformation. If this is different from 0, you get a symmetric matrix, which is a measure of the local deformation of your body. Okay? How many independent components you have in a symmetric matrix? You have the elements of the diagonal and 3 elements outside the diagonal, because the other 3 are equal. Okay? So you have 6 numbers which characterize G. In order to measure deformation, you need 6 numbers. This G. Okay? So, you take 2 vectors, V and W, which are 2 segments of material particles. Okay? They can be unit. Why they can be unit vectors? Because when you have chosen epsilon, you multiply everything times epsilon, and thus everything is linear. It is the same. Okay? So, what means GW inner product? V. You remember what is G. So at the end of the story, if you take 2 vectors V and W, and you consider GW inner product V, this is equivalent to calculate FV dot FW minus V dot W. Okay? So, W dot GW is equal to FW dot FW minus 1. Because W dot W is 1. So this is the square of the length of W. So this is a measure of elongation. This is how much FW is long minus squared minus 1. So, the elements of G along the diagonal, if you choose a basis here, E1, E2, E3. EI dot GPI, you know, it is GII, the component along the diagonal of the matrix representing G. And this M&MO is what? Is FEI dot FEI minus 1. FEI dot FEI is the length squared of EI in the actual configuration. So it is how much the segment EI is long in the present shape, minus 1, which is the length before deformation. This is a measure of the elongation of EI in the actual configuration. So the geometric and mechanical meaning of GII is clear. Okay? If instead you consider EI dot EJ, so GJI, then you have this, and what you have here? You have EJ dot EI. 0. Okay? Now, what is this? This is FEJ length, FEI cosine of theta EJ. So the element outside the diagonal allows you to estimate the new angle between two vectors. They were orthogonal before deformation, they are not orthogonal anymore. And the cosine of the new angle is given by Gij divided by these two lengths. Okay? I'm sure that when you studied vectors in physics, they told you mass density is measured by a number. The distance between 2 points is measured with a number. You need the unit of length. However, there are quantities which cannot be measured with numbers. You need vectors. So a displacement or a force. If you say I exerted a force of 10 newtons, this means nothing. You must tell in which direction. So in order to specify the physical quantity force, you need a vector. Okay? Now we are meeting a new guy. We are meeting a quantity, deformation, which is not described in terms of a scalar. It's not described in terms of a vector. It is described in terms of a linear map. Deformation is described in terms of a linear map. So, the the word deformation. The phenomena behind the word deformation are modeled by means of this tensor G. Is this true? Really true? When Cauchy said that this is the only deformation measure, everybody believed him, and there was only one voice against him. Viola said that this is not true, because not only G is characterizing deformation, but also gradient of G. So let us try to understand this. I want to tell you that I will try to go in some details. If you want to study the composites used for building the airplanes now, you need to use the theory of Viola, not the theory of Cauchy. Why? Because G gives you some information about the deformation. It is not telling you all the story. So, if you have your cues, let us talk with intuition, then we write formulas. So, this cue is deformed how? How it is said by G of this coin, of this point. Note, this other cue is deformed by the value G you have in this other node. So you have a field of G. Okay? But nothing is telling you how G is varying, moving from one node to the other. So there is no reason for considering the field G alone. You must consider also gradient of G. Why stopping at the first? You could need to go up to the end gradient of G. So to get a complete description of the deformation of one cube, in general, you may need not only the value of G in this point, but also the gradient of G in this point. The second gradient of G up to the end gradient of G. Now, I will try to go into the detail of this because I want to make you understand this point. When Viola wrote this, Poisson answered that this is useless mathematics. There was a violent controversy, at the end of which, as Viola died, being 50 years old, while Poisson survived him many decades, of course, he was loser. So, continuum mechanics developed ignoring all higher gradients of deformation. And engineers believed that this was generally true. So I want to underline it. There are some bodies for which the deformation is very well measured in terms of the quantity G. If you take a metallic beam, homogeneous, this measure of deformation is perfect. However, as I've shown you this morning, if instead of taking a piece of metal you consider a tissue made of woven fibers of carbon, then this deformation measure is not good anymore. You take a theory in which the deformation is measured by G, you do a lot of work, you do a numerical simulation, and the wings are not going up, which is a macroscopic effect of an assumption which is very serious. So now we have to go into the detail of the Cauchy theory, and then we have to improve Cauchy theory. Okay? I have organized this lecture in such a way that now, for the next minutes, we talk. Tomorrow morning, we wake up, we are stronger, and we talk about mathematical details. Okay? So the mathematics of today is ended. How do we find equilibrium configurations for a mechanical system? We go back to Galileo Galilei. This is, imagine to have a wire of metal and to have a small ball which is falling. So this is a mechanical system in which you have only 1 degree of freedom, the coordinate of this ball along this axis. So you characterize the position of this ball with this abscissa. Okay? You have gravity, so you have a potential energy, the interaction of this ball with respect to the gravitational attraction with the Earth. We know that this is experience or some theoretical knowledge which somebody told us. That this ball must be in a minimum of energy for having stable equilibrium, or in a maximum of energy for having unstable equilibrium. If you give a little, if you impose a little disturbance to this ball, so you move it or you give a small velocity to it, it will start moving in this way until friction will oblige it to go back to the minimum. Instead, if you impose a small disturbance starting from an unstable equilibrium position, this ball will do a lot of you go down, up, down. You move back and forth in a very complicated way. So, if you want to find equilibrium, you must find the potential energy. And then look for minima. So this is a general conceptual scheme which has to be conceived in order to develop a theory. We can amuse ourselves thinking that this is a meta-theory. The theory which is teaching us how to build theories. Do you want a theory which is working? Then you must find at least potential energy. If you find potential energy, you can characterize equilibrium looking for the minimum of potential energy. If you want to study the motion, then you must find also kinetic energy. And then you are obliged to minimize action, which is the difference between kinetic energy and potential energy. These ideas are Italian. Lagrange is an Italian mathematician who went to Paris to have a good career, which happens very often to Italians. His true name is Lagrangia, which is the Italian name. He changed into Lagrange. And this, when you write in English the adjective Lagrangian, you write with the I, not with the E. If this is his name. Okay? Piola was a follower of Lagrange, while Cauchy was the beginner of another philosophy, and Poisson was a follower of the philosophy of Cauchy. So my suggestion is not to read the other chapters of Dartin because he's a follower of Cauchy. We must be followers of Lagrange. The reason is that you cannot invent anything new with the approach of Cauchy. Everything new which has been invented with the Lagrangian approach. When you have a new phenomenon, you want to find the mathematical model for the new phenomenon, you must look for potential energy. You must look for kinetic energy, and you must minimize action. This is not my opinion. The physicists who have this opinion are Landau, Feynman, and many others. Landau is famous. I don't know if you heard this. Maybe the best Russian physicist. Feynman got one Nobel Prize and many prizes, and is the inventor of new parts of quantum mechanics. When they wanted to invent quantum mechanics, they needed to look for the action. So when you need to invent a new theory, you need to find the correct expression for action. Okay? Now, the problem is, which is the potential energy for a deformable body? So before resting for today, we try to understand this. So, where the Platonic idea of our body. This body is placed in space with current. And this body is subjected to an external action. So there is a potential of this body. For instance, if you have gravitational force, this body is subject to potential energy, gravitational potential. So, in the standard expression for potential energy, we must include deformation energy. This is a part of the energy. If we call the reference configuration C star, the term to be added to the potential energy for your body is integral over the Lagrange configuration of a deformation energy, let's call it E. The integral is over the volume. What we have to place here. If I have a small cube which is changing its shape, to which quantity you think we should consider that the deformation energy is depending? The painfully introduced deformation energy. So when you count all energies around for finding minimum of energy, not only you must consider all the forces applied to this body by external world, gravity or others. But in order to consider every energy, you must add deformation energy. If you have a spring, you pull it, you are storing some energy in the deformation of this spring. And this energy is depending on the deformation of this spring. Okay? This is what we already do. This is not, again, only my opinion. There is a German scientist called Hellinger who wrote, I think in 1916, the article about continuum mechanics for the Encyclopedia of Mathematics of Springer, and Hellinger writes explicitly that this expression for deformation energy is due to Viola. Okay? So, looking for the minimum of energy, so looking for the equilibrium configurations of a deformable body, you must include in your model a term including deformation energy. Now, the idea which we have is the following. We introduce a volumic energy of deformation, and this volumic energy of deformation depends on the local measure of deformation, capital G. Do we have done everything? Viola says, this is a class of materials. We can call it first gradient materials. Why? Because in G, if you remember, G is F transpose F minus identity. In F you have gradient of placement. So you have a deformation energy which depends on the first gradient of placement. So we can call this first gradient material. Is this model good? Until this model is giving good results, we use it. However, for logical reasons, in general, we must be ready to add grad G grad energy in the expression of deformation energy. What I want to say that this cube has a deformation energy which depends not only on G, but also on the first, on the second, on the nth gradient of G in it. So in general, the energy which we are looking for requires a dependence on the nth gradient of G. Okay? In which case we can call it n plus 1 gradient continuum. Because grad n of G includes n plus 1 gradients of T. Okay? I don't know why a group of mechanicians refuse to consider this dependence. They claim it is impossible, it is physically not meaningful. Landau writes his book with n gradients. Sedov, a big Russian mechanician, wrote with all gradients. In Poland, I know for sure that Sobolowski and Blinowski of the EPPT one considered many gradients after the first one. So there is a group of persons who are followers of Viola and a group of persons who claim that these terms are impossible physically. I cannot imagine how you can describe the behavior of composites without adding this there. But this is controversy. So what we will do next? We will consider first gradient materials and we will study them. Then we will try to study second gradient materials. I have a written text about this, so I can give it to you. Okay?